All right, so we just finished having a nice problem where we took the delta H from tabulated values, delta S from tabulated values, and we calculated what a delta G was at a given temperature. All right. Now, given that we have this delta H and I have our S value here for our chemical reaction, is the reaction favored at higher or lower temperatures?
Well, do we use that equation?
Yeah, we can use that equation, right? What's the equation that relates to favorability or spontaneity?
Delta G equals delta H minus T delta S.
That's right. Delta G equals delta H minus T delta S. Okay? So, if delta H here is a, what, positive or negative value for this scenario?
Negative.
Negative value here. Delta S, positive or negative?
Negative, but it's a small negative.
That's right. It is negative, though. So, temperature, is that a positive or negative value?
Oh, that's a trick. I know it's always positive, temperature, Kelvin.
That's right. It's always positive. But as we get a larger value here, I'm going to subtract this negative, and so that makes our reaction a positive, the contribution from this side, positive value, right? So the larger the temperature, the larger the positive value that's going to be added to this negative delta H. And again, if the reaction is spontaneous, then what's the sign on the delta G?
It has to be negative.
That's right. Very good. So is the reaction favored at higher or lower temperatures?
I thought reactions were favored at higher temperatures.
Well, that's kind of what we're seeing here, is that it depends on whether the delta S is a large positive value or a positive value, or in this case it's a negative value. If it's a negative value, then at large temperatures, this value, this component will contribute a large positive value at large positive temperatures, making the delta G, decreasing the likelihood of it being a negative value. So, for this reaction, delta G is going to be negative at lower temperatures. So, at different temperatures, your delta H, or your delta S, not your delta S, but your T delta S contribution can change. All right. If the system is not standard, thermodynamics can still apply. Or in other words, we have ways for dealing not with just different temperatures. We can also deal with different concentrations of materials. And our delta G value equals our delta G naught plus our, so like we said before, delta G naught, or delta G will equal delta H naught minus T delta S naught at any temperature. This will be equal to whatever that temperature is. Another interesting relationship between delta G naught, right, at standard conditions, delta G naught, and delta G at non-standard conditions is this statement here. Delta G at non-standard conditions is equal to delta G at standard conditions plus kind of a correction, where we take R, this gas constant, to make our units work out, the temperature, and the natural log of RQ. Now, do you remember what Q is?
Q is the quotient, right?
Yeah, the quotient for the chemical reaction. So, our reaction quotient, we can then use delta G equals delta H minus T delta S, where this delta H naught minus T delta S naught represents our delta G naught. And we can find delta G by adding on this, again, this kind of adjustment of RT ln Q, where Q again is our quotient. Okay? So this allows us to make sure that we don't neglect our temperature, and we also don't neglect any variations from concentration away from standard state. So let's look at this one and go through it together. Given that delta H is this value, S is that value, the pressure of HCl is 2 atmospheres, and that of the water is 1 atmosphere. What is the change in free energy for the reaction at 500 Kelvin? All right, well, we can put in our delta H naught. We can put in our delta S naught. We can put in our temperature, which is going to be 500 there. So essentially we're going to go back and look at this value here, negative 36.5. And this portion right here is going to be negative 36.5. We can jot that down for ourselves. Plus RT ln of Q. Now the Q for this scenario here, so here we have our 97.3, we have our 500, our 0.122, that's equals to our 36.25. Did I copy down the wrong number? I thought it was 2, let's see, 36.5, either way, close enough. So that gives us our 36.25. And then we can add our RT ln of K, where our Q then equals, this is a solid, so that's not going to be in our equilibrium statement, or sorry, not equilibrium statement, our quotient for the reaction. This is a solid also, but this value here is going to be 1 atmosphere. This value here is going to be 2 atmospheres. We're going to square it. Let's write down again the Q for this chemical reaction. It's products, concentration of water raised to its coefficient over the concentration of reactants, HCl, raised to its coefficient. And when we're talking about concentration in terms of gas, that's pressure. So we have our atmospheres, 1 over 2 squared, that's 0.25, 1/4, right, 0.25. And so I can add this natural log of 0.25. I can add this RT, there's our R value, there's our temperature again, and the natural log of 0.25, and get our adjustment on the actual delta G for this reaction. Now we did those together, so I don't expect us to be able to kind of do that individually. But it's very interesting stuff here, that we can identify the spontaneity of a chemical reaction with the delta H, with the delta S, and then with an adjustment for a change in the quotient concentrations. Now, how does this delta G relate to equilibrium? Well, we can also have this relationship here, where delta G naught equals negative RT ln of K, where K is our equilibrium constant. This can be rearranged. K can be brought over here, natural log, which is the log of E, right? We can get rid of it by raising E to the rest of the stuff. Our equilibrium constant equals E to the negative delta G over RT. So this is a nice, significant equation that allows us to relate the rate, or sorry, the equilibrium constant, K. Now, do you remember the equilibrium constant?
Yeah, I remember it.
It allows us to relate our equilibrium constant to our delta G for our reaction. Okay? This can be parsed up into this delta G here, right? Delta H over RT plus delta S over RT, right? And then the natural log of K could be taken. So we have a handful of other options for us. We're not going to pay much more attention to this information here, but this equation here relates our equilibrium constant to the spontaneity of the reaction, or our delta G. So we would like to determine our equilibrium constant for a given chemical reaction at 2 different temperatures here. Well, how do we get to the spontaneity, sorry, no, the equilibrium constant from this information down here?
Well, look, can I see that equation again?
Let's copy it down for ourselves. What does that show us?
The equilibrium constant, or the equilibrium constant is equal to e to the negative delta G RT.
All right. K equals e to the negative delta G over RT. So, can we get our delta G somehow?
Yeah, we could just do it at 298 at least. We could just do products minus reactants for delta G of formation, right?
Yeah, we could. We could. We could just take the calcium oxide, negative 604.2, plus the carbon dioxide, negative 394.4, and then subtract our negative 1128.8, and that would give us the delta G of formation. What would be the advantage of finding the delta G instead of looking at the delta G of formation by looking at the delta H and the delta S?
Well, because then you can use a different temperature.
That's right, and that's what we need to do. So let's look at the delta H, all right? Again, products minus reaction from our tabulated values. Let's look at the delta S, same thing. We recognize that this is in joules and not kilojoules. And then delta G, we have our delta, this is finding the delta G at 298, which is what we talked about. Products minus reactants. And then we can get the delta G at 298, but then we can get it at 500 by taking our 178 minus 500 Kelvin times our delta S, right? That gives us 97.8 delta G at 500. Now, what do we do with these delta Gs?
That equation down there?
That's right. We can take these delta Gs and we can take K equals e to the negative delta G over RT. All right. So if we do that, we see that we get some K for 298 and a K for 500 degrees Celsius. Both of them fairly small numbers, meaning that this reaction it's at equilibrium is mostly what? If these are very small numbers.
Mostly reactants, small numbers.
That's right. Small numbers, mostly reactants. How does the equilibrium shift as we add temperature in this reaction?
At K500, it's the 6.06 times 10 to the minus 11. Is that what that says?
Yep.
And then the 298 is the 1.5 times 10 to the minus 23.
Yep.
So I guess at higher temperatures, you get more products?
That's right. Higher temperatures, you get more products. What would you say? Was this reaction then, in terms of equilibrium, or in terms of releasing heat or requiring heat? What do you think?
Well, like if we said that we heated it up, we would shift the equilibrium to the right. That would mean heat was acting like a reactant.
That's right. You remember that business? Where we have this chemical reaction, CaCO3, going to CO2 and CaO, right? If we saw that, and this is in equilibrium, let's say, if we saw that we heated this up and the reaction shifted to the right, then that would be an indication that this was an endothermic process, that heat was being consumed by the process, and that's why when you add heat, raise the temperature, it shifts to the right. Now, we've always looked at that from a delta H perspective and said, what's the delta H? If it's positive, it's an endothermic reaction. If it's negative, it's an exothermic reaction. If we see that raising the temperature decreases the K value, right, or sorry, increases the K value, makes it a larger value, wouldn't we expect the delta H to be a positive value?
Yeah, I guess. Is it? Oh, it is. It is.
Yeah, see? We see that the delta H is a positive value. So for delta H equaling 178, what we had talked about before still is consistent, that an endothermic process requiring heat, you add heat, it'll shift the reaction to the right, shift the equilibrium to the right. Okay, good job. Lots of neat stuff.